Hello, and welcome to the latest episode of Data Unchained. I'm your host, Molly Presley. If you're not familiar with Data Unchained, let me tell you a little bit about what this podcast is all about. The paradigm for data access has changed. In today's decentralized world, getting data to remote workers, to distributed applications, and multiple cloud regions is a real challenge. Data Unchained digs into the challenges as well as the solutions to help make data an asset as a globally available resource. Today, I'm really excited about our guest. We have Trond Myklebust, who is the maintainer of the Linux kernel for the NFS client, as well as the CTO for Hammerspace. Trond, thank you so much for joining us.
Thank you for having me.
And I was excited to hopefully get your last name right. I'm embarrassed to say I had to check before we started recording to get Myklebust right in English. How do you say it in Norwegian?
Usually Myklebust.
Okay, excellent. So Trond is located in the U.S., here in Michigan. Did you live in Norway as part of your childhood?
Not as part of my childhood. I actually moved to Norway when I was 21 years old in order to start a Ph.D.
So what was your Ph.D. in? Can you tell us a little bit maybe about your educational background, and then we'll talk about work?
Sure. I'm originally educated as a physicist. So I was actually working on a Ph.D. in particle physics when I got attracted to working on the Linux kernel. I ended up actually abandoning my PhD, unfortunately. After doing all the fun bits, with all the experimentation, got to the part where I had to write up a thesis. It turned out that writing code was a lot more fun.
Interesting. I was trying to figure out what the tie was from particle physics to Linux kernel maintainer, and it was the code writing that attracted you.
Exactly, yeah.
So can you tell us a little bit, how did you get started in the Linux community, and how did you move all the way up to a role of being one of the maintainers?
I was working on my PhD, and one of the jobs that typically sort of falls to the PhD students in your typical particle physics environment is running the computer hardware. So I was helping to manage our systems, which at the time were based on sort of VAX VMS systems. And then we sort of started looking at being able to use cheaper hardware, basically commodity Wintel hardware. There was this new operating system that was starting to gain traction out there called Linux. So we started playing around with it. Found out fairly quickly that this was actually something that was much cheaper than buying these expensive X terminals that you needed in order to operate against the VMS systems. And then, we started wondering what else we could do with this operating system and these cheap computers that we bought. And it turned out, there was all sorts of things available, Fortran compilers, that sort of thing. So we started using them for our development purposes. Particle physicists spend a lot of their time basically developing analysis software in order to run through these huge files of data in order to dig out the statistical information from them. And I basically went to my supervisor at one point and said to him, I think we can use these things, basically replace a lot of our VAX systems with them. He came back to me and said, yeah, I think you might be right, but I'm having some trouble with some of the software. Specifically, he was trying to use these computers to read his mail. And at the time, the mail boxes at the University of Oslo were being served through this protocol called NFS. So I started looking at what might be the problem there. And before I knew what had happened, I was starting to delve into the kernel and messing around with the code there and trying to fix the various bugs that we were encountering at the University of Oslo. So at some point, I started reaching out on the mailing lists where kernel developers hang out and said, look, I've got these fixes. Would you like to take them? I got in contact with some of the top developers at the time, Linus himself, one of them, and a developer called Alan Cox, who was, at the time, Linus's number 2 developer. He was basically taking care of testing a lot of the fixes before they went into the upstream kernel. So I sent him a bunch of patches to fix a few things. He took exactly one patch. That happened to be the patch where I had sent in my contact details and said, I'm willing to maintain these patches I just sent you. He wasn't interested in the patches themselves. He just took that maintainer thing and sent that to Linus. And suddenly I found myself in the role of being a Linux NFS kernel maintainer.
Interesting. Don't always get what you ask for. But as you've moved into that role, I think it would be interesting for people to understand, what does a kernel maintainer do? Are you the gatekeeper of what goes in and what doesn't? How does the community decide which patches actually do go in as they start to create them?
Yes, so the role of maintainer has changed a lot in the last 25 or so years. When I started, I was basically the main developer for the patches. I'm still heavily involved in developing, but it wasn't so much a gatekeeper role, because that role was typically held by Alan Cox and Linus himself. But obviously, as the size of the kernel has evolved, as the community size has evolved, we've had to scale. And so while the maintainer role was, as I said, originally mainly a developer role, it has now sort of turned into this gatekeeper role, with a number of maintainers taking patches from the community in general, proof checking them and doing whatever we can to test them out, and then sort of sending them on to Linus himself. So you've got this tree of maintainers underneath Linus.
And Linus still looks at all these final decisions even today?
My understanding is that he's sort of slowed down a little bit on that, because there are typically the number of patches that can go into just a single release of the kernel can number in the tens of thousands. Oh,
wow. That's a lot for one individual, for sure.
Right.
But he's still pretty involved in at least the macro level of these decisions.
Yes. And he will typically sort of sample at least some of the patches. And, if you have done something that he doesn't agree with, he will make it very clear to you that that's the case.
Cool. So before we talk a little bit more about NFS and the Linux kernel, can you talk a little bit about how you've moved into industry, and you maintain a dual role working in industry as well as in the Linux community, and kind of how those two come together?
Right. So when I started, I was doing my Ph.D., so I was 100% working on a hobby basis on the Linux kernel. And, what happened was a company, turned out to be NetApp, reached out to me and said, you're doing good things for some of our customers. Would you like to come visit the US and participate in some of the testing events that we have here? And so I accepted that, got in contact with some of the people developing NFS for a living here in the US. Before I knew it, as I said, I was sort of getting dragged into that community as well. I was nearing the end of my Ph.D. As I said, I was writing my thesis, and I was starting to run a little bit over the allotted time. So I was starting to run a little low on funds, and ended up reaching out and sort of asking, would you like to sponsor me? And that turned out to be the gateway drug that pulled me into the industry.
And you were at NetApp for quite some time, working in various positions, as I recall.
Yes, I was there for 9 years.
And then, now you've moved on, you're working in Hammerspace, but in a similar kind of role, right? Where you're spanning both the Linux job as well as working as the CTO for Hammerspace?
Correct, yeah. So that's become a more common role over the years. A lot of the kernel developers have had to turn to industry in order to make a living, a career out of their work. So what's happened is typically the companies in question will either outright sponsor the person to do only maintainer type work, work for the community, or they will sort of have this dual role type of arrangement, where you spend some of your time working internally for the company and for the company interests, and then you get a certain amount of time to allocate to work purely on a community basis.
Let's talk about the NFS client. I've worked in the storage industry for quite some time, largely in vendors who use NFS as a target. Talk a little bit about, if you would, how the NFS client software works as people use the functionality to make it into pNFS. How is that different? And maybe just give everybody who may not be super familiar with this part of the code a bit of an overview of how that all works.
So the Linux NFS client should, when it's working correctly, basically be as transparent to the user as possible. It sits underneath the POSIX application interface. And so your typical user will do all the usual application programming that they will do for local file systems. They will open the file, they will read the file, they will write to the file. Underneath the covers, what is basically happening is that the client is converting that into remote procedure calls that go to the server and execute the operations that are required. What's happened in the last 30 years is that as the industry has changed from very much a set of workstations, large workstations with lots of users, relatively small numbers of workstations, into a setting where you have data centers with huge numbers of clients, each one operating against the same server. The requirements for how the NFS client has to operate have changed. So originally, NFS v2, NFS v3 were stateless protocols. They operated mainly in a simple way as possible so that if the server went down or something happened, it was easy to just pause the application until the server came back up again and then continue operation. While that makes for an easy implementation on the client and on the server, it doesn't scale very well. Once you get to sort of several thousands of clients, your server typically wants to be able to know a little bit more about what the client is doing so that it can do things like prefetch data, cache data, and manage the data. So the last 20 years, we've been developing the NFS v4 protocol, and the main purpose has been to basically adapt NFS to the modern use case of large-scale operation, high performance, and being able to operate in diverse environments, data centers, the cloud, etc.
Largely, I think most organizations and architects think of high performance as requiring some kind of parallel file system client where you're loading something on the client that has an ability to communicate directly with the server client, so to speak. How does NFS fit into that world today with 4.2?
The original NFS v4 protocol did not actually include any form of support for parallel file systems. That's functionality that was actually added in the first so-called minor version of NFS v4. And because there were several different models for how the various vendors that were involved in the standardization process wanted to work, it ended up being sort of a little bit of an add-on to NFS rather than sort of deeply integrated. And this has actually turned out to be a positive thing. Originally, there were 3 different models for how people wanted to add parallelism to NFS. There was the blocks model, there was an object model, and there was an NFS model. Basically, in the blocks case, people wanted to be able to address drives directly, send SCSI commands to read and write data. In the object model, it was more like the modern object store. You send put and get commands, and you have your storage is slightly more abstracted. And then the third case, as I said, was NFS as the back end, where you basically have a number of NFS servers acting as data stores and basically serving up reads and writes as far as the client is concerned. And what resulted from that inability to standardize on one model was a model where the abstraction between metadata and data is very clearly defined. In the case of metadata, all the metadata goes. The traditional metadata server does all the opens, it does all the closes, that sort of thing. And when the client wants to go talk to the data servers and read and write data, it'll go and ask for a layout, which is basically can be considered to be a map of where the data is located and how to access it. And because of the requirements of things like the block storage, the SCSI storage, there were a number of features that were added in to allow, for instance, the metadata server to say, I'm going to recall the layout, I'm going to ask you to temporarily halt I/O so that I can do some form of management operation on the data server. And then you can ask for another layout and continue your I/O. And this basically means that the pNFS model has built in an ability to manage data on the fly, which turns out to be sort of very useful for all sorts of purposes. We use it in Hammerspace to be able to do tiering, and in order to be able to sort of separate out replication of metadata and movement of data across different sites.
That makes me wonder, as you talk about some of the capabilities which Hammerspace takes advantage of, and that there's been a variety of contributors, how standard is pNFS in the industry right now?
It started out with 3 different companies being unable to sort of standardize on one protocol. At this point, instead of sort of consolidating, we actually have 3 more models. So there's the original blocks of object and NFS v4 based layout types. In addition, there is now a second blocks based called SCSI, which basically differs from the original blocks by the way in which clients discover the storage nodes. There's an NVMe based protocol, which is designed to take advantage of the newer NVMe protocol and the RDMA functionality that provides. And then there is the Flex Files standard, which Hammerspace promoted and which allows you to basically use NFS v3 as your backend storage.
So it's 4.2 on the front end of the client and v3 on the back end of the storage?
Correct, yes.
Interesting. Okay, got it. With all these different perspectives on how to leverage this capability, NFS and Linux itself has a massive community. Is this the technology that's primarily being used in research environments? Is it enterprise ready? Where do you see the maturity of NFS, specifically the parallel NFS capabilities right now?
It took us a while to develop both NFS v4 itself and then the pNFS capabilities. When we started with the NFS v4 development, we were basically starting from a stateless protocol. And we had to learn how to work with stateful protocols. And it turns out that NFS v4, for various reasons, is a bit more complex than most protocols because it needs to inherit a lot of the features that came from NFS v3 with respect to being able to recover from reboot situations and outages and that sort of thing that it turns out are not uncommon in data centers, but which can have a big impact on your data if it causes you to have to restart all your jobs. So it took us about a decade, I would say, to sort of get NFS v4 to the point where people felt comfortable promoting that as the standard way of mounting NFS And then pNFS, obviously, because it is an extension of NFS v4, then had to develop as well. We had to deal with the complexity of the fact that there are 6 different standards for it. So you need a level of abstraction at the kernel level in order to be able to deal with that. There was the complexities of dealing with recallable layouts and avoiding a complete halt of I/O when the server actually wants to recall the layout and do management. It's taken us a few years, both on the client and the server side, to figure out how we want to do this. Not least because part of the problem was that with the protocol itself being designed in the ITF, there was a certain amount of prototyping done, but anybody who has done prototyping and of storage knows that once you try to put that knowledge into practice in large-scale industrial environments, enterprise environments, that you then will hit all sorts of corner cases which you thought were rare and that need to be handled often, just through the sheer volume of requests and data that's being processed. It's really taken us another 10 years, really, to get pNFS itself to the point where we believe enterprises are able to feel comfortable putting their data on that kind of storage.
So I know in some of the Hammerspace customers that I've seen running out in production, they've been using this pNFS capability. What kinds of industries, maybe even in the broader Linux community, are you seeing putting the NFS and pNFS 4.2 capabilities being put into production?
A lot of the kernel pNFS implementations tend to be very simple and go for the block-based pNFS solution rather than the more complex object and NFS-based solutions. The reason is that in the case of block storage, your metadata server can be relatively simple. It doesn't need to coordinate a lot with the backend storage. It's simply serving up SCSI block data as part of the layout, and then the client is doing its I/O as necessary. With the object and NFS-based storage, things get a bit more complicated because you have to have an architecture where the metadata server and the data servers are able to communicate with each other. And the NFS protocol itself does not specify, deliberately so, how that back-end communication is supposed to happen. So for companies that have implemented the files back-end, for instance, they tend to be using their own proprietary back-end protocol, which means that you cannot typically use a generic NFS store as your back-end storage. It has to be built as part of the server from the vendor that built the metadata server. So in practice, there has only really been commercial implementation of the files, so the NFS v4.1 based backend, that's been NetApp. With the Flex files, the NFS v3 backend, Hammerspace has produced an implementation, and there are 2 non-commercial implementations that I'm aware of. There's one non-commercial implementation in the FreeBSD kernel, and another one which is actually Java-based and was built by the particle physics lab in Desi in Hamburg, Germany.
When you think about, probably with your Hammerspace CTO hat on a bit as well, what's being pioneered upstream by Hammerspace and any of the other contributors that you're able to speak about right now?
So the big innovation that Hammerspace brought was basically the introduction of the flexible files pNFS backend. What it has done is it has basically married the NFS and the object backend models. And indeed, it was originally implemented as a successor, not so much to the NFS files backend, but as a successor to the object model. And What it enables is basically for the metadata server to take any NFS v3 server and use it as a backend storage. There is no need to coordinate really between the metadata server and the data server because there is no state that needs to be established. Once you have a file available on the data server, then you can already start to do I/O and you can do reads and writes without any further ado.
So Trond, I think as you think about this related to the Hammerspace technology, that there's a lot of under the covers automated replication related to both metadata as well as data occurs. Can you talk a little bit more deeply about how that model works?
pNFS enables separate management of the data and the metadata thanks to the separation within the standard of the layout versus all other metadata. And what this means for Hammerspace is that we can basically treat the two different types of data differently. We can replicate metadata on the one hand. Typically, the metadata tends to be compact. It tends to be easy to replicate quickly, which is really what you want on the client side, since the client is looking to discover files, directories, etc., so that it can open them. Whereas the data itself can perhaps move a little bit more slowly, depending on whether or not the application is actually trying to access the data at the time, or if it's just planning to do so at some point later in the...
You know, as I've been listening to you talk about the evolution of Linux from kind of the early days on through to the very mature space it is today, it kind of reminds me of some of the evolution that occurred in the Ethernet space, that Ethernet was a standard, but it really wasn't a performance network. There was some evolution that needed to occur to make it what it is today, where it's gone back to being a standard with 100 gig Ethernet. It's fast, it's reliable. But as kind of a stopgap, there was some proprietary and different technologies that came in, like OmniPath and InfiniBand. Do you see an analogy in the Linux space of some pieces that needed to be added in to give the performance and the enterprise capabilities to really make it a standard again today?
The whole notion of a parallel file system went through that process to a certain extent. If you look back 20 years ago, there were several parallel file systems that were being built. IBM had GPFS, Panasys had pNFS, and there was Lustre. All of these parallel file systems that did not interoperate, they required, to a certain extent, proprietary clients. They required different management systems. They were typically niche products that would be deployed for a specific HPC workflow, but couldn't be really deployed as your general infrastructure, simply because they required modifications to your kernel. They required, in some cases, modifications to your application, that sort of thing. The desire to standardize was really what brought these companies into dialogue with the NFS community. And I remember in 2004, we had a series of meetings between the different stakeholders and the IETF NFS v4 group in order to be able to extend the protocol, in order to add in support for parallel file systems. This led eventually to pNFS. It led to a protocol that supports multiple parallel file system architectures, but it integrates well into existing management infrastructure. It can use all your existing storage infrastructure, typically.
So that sounds kind of like a utopia for architects and IT groups who are trying to figure out how to build these high-performance workflows and still be able to integrate it into their enterprise IT standards and as far as security and compliance. Is that the right way to think about that?
probably is. I mean, the point that I'd like to make is really that enterprises typically already have a whole set of infrastructure for monitoring and managing storage.
So does this make it easier to fit in with the IT infrastructure and IT rules that are in place in most enterprises today?
Yes, because most of them are already set up to deal with NFS as a storage protocol. They typically have virus scanning, they have firewall rules, and they have sort of management scripts, etc., that sort of thing, that needs to integrate with the storage that they don't want to necessarily change every time someone comes and brings in a new parallel file system, high performance file system.
Yeah, that makes perfect sense. Kind of tying back to making it not just enterprise ready, but enterprise adoptable. Fitting into all the infrastructure they have in place is really important. All right, Trond, this has been really insightful and a great way for us to get a better understanding into how the evolution of this capability has occurred over the decades. I know that a lot of organizations are anxious for this functionality, and I appreciate you sharing some insight in how to take advantage of it in their workflows today. Thank you so much for joining.
Thank you.
Thanks for listening to Data Unchained, powered by Hammerspace. To learn more, visit hammerspace.com. If you have a guest you would like to hear on the show, email me at molly@hammerspace.com.